All right, let's get started. I don't think today's lecture is going to take the entire time, just because I was going through it. It's not going to take me a very long time to discuss it. My goal with the leftover time in class is to potentially start working through the homework. I do want to remind you that I am still working with the tech people to get it to connect to our Canvas site, but it doesn't mean you don't have access for homework. Right now, there are 3 homeworks open, so I think some of them are combined with other sections. I know one of them is, we're gonna tell you again tomorrow, so you don't have to do it yet. But all of last week's homeworks are open right now in Canvas, not in Canvas, in Macmillan. You can access Achieve by going through our Canvas site and clicking on the Achieve module and just go to Achieve and you can start working through it. I'm only saying that because it's not in front of your face. It's not blinking at you like you would if it was on connected to our Canvas site, which is frustrating me. So that's why I'm calling Macmillan every single day, trying to get it to work. We have 2 papers. I'm gonna grab them right here, right here. So just reminders, if you haven't at least linked your Achieve to Canvas, go ahead and do so. And the second, Macmillan allows me to throw it into Canvas more regularly, but it's still open and they're due at the beginning of our exam. So right now, it's due June 13th at 11:59 a.m. My advice is to do a little bit every day, or if we have leftover time in class and I shut off the lecture, get out your computers and we can work through it. And that way you're we're doing like this open classroom. I can be here to answer questions. That's my goal for today. Any questions on that? Okay, I did open up your first quiz. What I do every single class period is I go and think about what we covered in class and ask a few questions in a quiz format. So it's the same concept where it's going to be due at the same time as your homeworks. So you have plenty of time to work on it. It's gonna take 30 minutes to do this, but do it at any time up until the exam. So the first quiz 1 is gonna cover what we covered in Monday and so if you feel really confident on, sorry, Wednesday and Friday. Really confident on those sections, go ahead. It's open notes, of course. My advice would be try it the first time without any notes so you can see what you're confused about. And then with the second time, you can of course do whatever you need to get the highest grade possible. But I will point out, like, there is a math question, just double check your rounding in units. So that's gonna be, yeah, that would be the main thing to do well on it. Okay. All right, let's get started. We are going to do binary covalent nomenclature, and then we are going to do a very little amount of 1.5. I do have a worksheet for us to work through. First, if you are online, I have this paperwork. This is like a cheat sheet. You can find this under the very first module under resources. So this is the nomenclature. I think I forget the next word on it, but it's nomenclature, and it's a great cheat sheet for what we're doing today. So I highly recommend having this with you, especially while you're studying and you're doing homework and things like that. The second one is going to be under modules for today's assignment. It's just an activity that we're going to cover today. So this is going to be under the Unit 1 module under 1.4. So we'll have some downtime today and we will work on this worksheet. All right, so binary covalent nomenclature. Let's review. We're going to be going into a little bit different direction. So previously we discussed they're unique. They have a very unique type of naming, whereas the other things we're getting into today will be slightly different. So I'm trying not to really confuse you. So that's why if you look at the cheat sheet that I passed out in class and pointed out online, it's like I forget what it's called. I don't know, but it kind of asks you some questions, like, does it have just carbons and hydrogens? So alkanes are only carbons and hydrogens. And that's why if it says, yes, if it's just carbons and hydrogens, you go down to the alkane naming. So that's the meth, the eth, the prop, and things like that. And we're only going to do the ane at the end. We're not doing ene or ine, just ane. Reminder, if you need to name alkanes or if you need to figure out what is in alkanes, this really helpful formula is going to be, I want you to get more comfortable with it so you can eventually memorize. So CnH2n plus 2. So the N represents how many carbons. So if it's, let's say, carbon, let's say a butane. So but 4, carbon 4. So 2 times 4 is 8 plus 2 is 10. So it'd be C4H10, which is butane. That is the chemical formula for butane. I also have the structural formula because I know when you get into organic, you're gonna have to start drawing things out. They're the same thing. It's just the structural formula just shows you how to draw it out. So if you have CH3 connected to a CH2, connected to a CH2, connected to a CH3. So same thing. If you count it out, still 4 carbons and 10 hydrogens. And then if you want to shorthand it, which we love to do because no one wants to spend all their time drawing out hydrogens, that is what we call a zigzag structure, where you're assuming on the end of it, there is a carbon. Any questions on that?
So the zigzag structure goes only apply to the alkanes?
Typically you can do zigzags on a lot of things, but if it's besides a carbon and a hydrogen, we tend to draw out the element. So on last week's Friday's worksheet, we had like a benzene. Sorry, if you're confused by what I'm saying, no worries. A benzene looks like this, where there's some double bonds mixed in. So you're still assuming that there are carbons at the end of every line, and you're filling in the hydrogens, you know, with where it goes. But let's say I have an oxygen. So this is still considered a zigzag structure. I know it's not zigzagging. It's just a shorthand notation of it, but if it's not a carbon or a hydrogen, we tend to put in those elements. And then we can't always assume, so we'll put the hydrogen on top of the, if it's next to an oxygen or a nitrogen. Yeah, that's a great question. Any other questions on alkanes? Okay.
When mentioned the like pineapple shows our metals from the campus stuff.
Yes, on under resources, I did, when we were in class on Wednesday, we kind of highlighted on periodic table elements where things were. Underneath the periodic table under resources, there's another one that says, you know, I forget how I named it, but it was metals, non-metals, all that. So there's two of them there where it goes over naming the columns, and it also goes over where the metals, the non-metals, and the metalloids. So if you have the periodic table of elements, the grayed out portion will be the metalloids, non-metals are on the right, metals are on the left.
And the metalloid is two, right?
Metalloid is a combination of them. So, but we typically don't really hit on it in Gen Chem. So that'll be more when you hit inorganic. So yeah, I might ask you in the quiz or in the homework which one is a metalloid, but we wouldn't go into details on their structures or bonding and things like that. Yeah. Yeah, and you're welcome. Any other questions? Feel free to blurt them out or put them in the chat. I'm here to answer everything. Okay, so if you have your periodic table of elements with you, I'd recommend getting it out. If you don't, we have a periodic table here in the classroom over there. If you're online, you can download the resource. It's under resources where it's at. So I just want you to get very comfortable on where things are. All right. So the next few slides are just us talking about elements. So for instance, here we have hydrogen, which is an H. So if you look at the periodic table of elements, they're not, I know not every periodic table of elements is as nice. They're not always going to say this is the name of the element. If you get one of those, I'm sorry, because sometimes it gets a little bit harder and I'm like, I forget what AG is. So sometimes it's really nice to have like, what is AG underneath it? So we have that here in the classroom. On our exams, I will of course provide you with a blank one. So I just want you to get more comfortable recognizing what is everything. So if I was to just say I have H, I might start getting there where I'm not always going to be like, where I have hydrogen. I'll be like, I have H. So you'll have to understand H is hydrogen, C is carbon. So some of these elements have 1 letters, some of these elements have 2 letters. It's just one's 1 letter, one's 2 letters. So yttrium is something that we haven't seen yet. I believe it's a metal. Where is it? Oh, yeah. What type of metal is that? Y'all remember? Transition metal. Yes, it's in that little block of transition metals. So that's something you might see on the quiz. I might say like, what type of metal is it? So yttrium is a transition metal. So it still just has 1 letter. Sometimes we might have letters. I guess, let me go back. Hydrogen is on column 1, but it's not a metal. So I want you to get comfortable. It acts like a column 1 in some ways, but it's not a metal. That's why it's green on our table over here. And that's why it's kind of you're seeing twice on y'all's tables. Carbon. Okay, so that's on it's a non-major group column. Fluorine. What group is fluorine in? It is a non-metal, but what about the column? It's a halogen, yes. But oxygen. It's a non-metal, yes. And it's a hard pronunciation. I don't think I'm saying it right. Chalcogen? We're all winners. Yeah, chalcogen. So I might throw something up there and ask you that. That's actually, there's gonna be a question or quiz that kind of similar to this. So if you haven't highlighted your periodic table of elements, you still have access to the one that I threw up in the helium. Ooh, helium. It's a non-metal. What is the column name? It's a noble gas, yes. Noble gases are very happy by themselves. They do not like to bond with others. So typically, if you see noble gases, they'll just be by themselves. Whereas with other elements, they'll have covalent bonding, ionic bonding. Calcium. Is it metal or non-metal? It's a metal. And what about the column name? Alkaline earth metal or alkaline earth I've seen. And if you are like myself, I am sometimes I don't have the periodic table of elements memorized. I have a lot of the elements I see most often memorized, but some like yttrium, I'm like, I don't know where to look. So it might take you a little bit of a while to look there. So no worries if you're kind of like looking and like, I don't see it, just take your time. First, I would probably start with the metalloids. And then if it's not in the metalloids, I look in the non-metals and then look at metals. Where's that? What column? Very bottom of column 1. So it's a metal and it is what type of a column name? Alkaline metal. Okay, osmium. Let's find osmium. Ooh, I see it. It's in the middle of the periodic table of elements. So it's a transition metal, yes. Ytterbium, YB, what is that? Where is it? Oh, it's in the, I see it, I'm sorry. It's YB, Seven? 70. What number is it? 70, yes, after 7. 70. It's like my brain is just not working.
Yeah, right.
Yeah. Lanthanide. See, it's like my brain just doesn't want to see it sometimes. So that is 70 on your periodic table, and that is a lanthanide. So it's still a metal, but it's called a lanthanide. I wouldn't ask you that, but fun fact, it is given to you on your periodic table of elements. Yeah, so you might be asked to like figure out things. There are some numbers that are on there that are going to be very relevant when we get to it, but being able to identify where things are at and identify what it is, that's going to be very, very helpful. Potassium, let's keep going. Potassium, what metal or non-metal? Alkali metal, yes. It's a metal, yes, and then it's an alkali. It's on the first column. And then silver, Ag. Transition metal. Gold, Au. Transition metal. Sodium, is it a metal or a non-metal? Column 1. Yeah. And then tungsten, W. One of the hardest metals there are. Yes, metal. What type of metal? Transition metal. Awesome. Things even I couldn't find, so great job. On the next slide, I do want to point out that the names are usually given by some scientists, but these names are the original names. They come from different, I guess, nationalities, maybe. Callium is Latin, so the L's represent the Latin origin. The GR represents Greek, so silver used to be argentum. So Greeks used to have like silver coins. Silver is just not a very good metal to have because it oxidizes so easily. It has some wonderful qualities, but it does oxidize very easily. So it's Greek, and then tungsten used to be wolfram. And that's probably where the W comes from. And then we switched to tungsten, and it's like, why is it W? Because it used to be, yeah, it's because it used to be wolfram, and that's Swedish in origin. So yeah, they all come from somewhere. And then when you get into the lanthanides, I mean, you start seeing, of course, like Madame Curie, she did polonium, she did dysprosium, so she was able to name them. So sometimes as you get further and further on, they start kind of naming them for themselves or someone they know, or the country, like polonium. But yeah, they have cool names. So we're gonna get more and more comfortable with this. You do want to definitely memorize what I'm about to say. Most atoms are happy by themselves, or they have, if they were to be by themselves, they'll just be by themselves. Metals are one of them. Metals are very happy. If I was to have iron by itself right now, it would just be iron. But there are several elements that are not happy by themselves. And those are going to be what we call diatomic. So Di represents two. Atomic is atom, so two atoms. So by themselves, they either want to bond with something else or they want to, I mean, that's the same thing. They want to bond with something else, whether it's or something else. So these will always exist. If it's by itself, it'll be two of them. So Dr. Patterson had this cool little saying of Brinkelhoff, because it kind of spelled out Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So if you want to think Brinkelhoff, I don't think I'm gonna do this on a quiz, like, but you're gonna start seeing it over them as a diatomic. So that's why they want to be bonded to something else. There are a few species that also want to bond with more than two, but we're gonna get to them in a timely manner. But this, I want you to get very comfortable recognizing the Brinkelhoff elements that are diatomic when by themselves. So that's why when you see oxygen, it's going to be O2 for oxygen gas. Hydrogen is going to be H2 for hydrogen gas. It doesn't exist by itself as individual hydrogens in the gaseous form. Memorize Brinkelhoff. Any questions on that? Now let's get into nomenclature and naming. So we have talked about carbon dioxide and hydrogen on the macro scale. So let's talk about macro, micro, and symbolic again. Macro is what we see with our eyes. So if I was to have just those elements, yes, are going to be diatomic all the time. If it's just by themselves, they're always going to be assumed diatomic. So yes, thank you. All right. So macroscopically, what do we see if I was to have, let's say, a clear beaker of carbon dioxide? What would you see? Nothing, right? It's just gas. We don't really see gas, but we would know inside this clear column that you'd have carbon dioxide just floating around. So macroscopically, you wouldn't see anything. What if I had a beaker of water? What would we see? You'd see a clear liquid. That's so you'd see something clear. It's very fluid. It can move around, doesn't really, I mean, it'll fit to the volume of the canister. But yeah, so that's macroscopically. Microscopically is when we think about it in a particle sense, in those circles. So we'd have like C. Yes, a double bond. would be with those particles. Symbolically would be just having the formula. Okay, so I do want to point that out because I might start asking more about symbolic versus, sorry, one second, macro versus micro. So C. I'm gonna put those lone pairs in there because they are relevant. All right, so this would be more of a micro because I'm trying to draw out what it looks like versus having just CO2 and H2O. So what type of bonding is found in these two compounds? Let's look at CO2. What type of bonding? There's a couple different answers, so we're probably all right. Double bonding, okay. Now, are these metals or nonmetals? So what type of bonding between the nonmetals? Covalent bonding. Okay, and then let's talk about this bond. Is it single, double, triple? Single. You can see the difference because I have one line for single and two lines for double. So what about covalent versus ionic? Are they metals or nonmetals? Non-metals. So what type of bonding? Covalent. So yes, they both have covalent bonding. So I would say covalent. Even if they have single versus double, they can still have very similar bonding with the covalent non-metals. What form do these compounds have on the micro scale? I kind of drew it. CO2 is linear, where this one will be more bent. What properties do these compounds have on the macro scale? We just discussed it, yes. CO2 at room temperature will exist as a gas. At room temperature will exist as a liquid. But what if I heated our room to maybe 150 degrees Celsius? The water would be a gas. Would CO2 still be a gas? Yes. The boiling point is, sorry, I'm thinking boiling point. The melting point of water going from a solid to a liquid is 0 degrees Celsius. The boiling point of water is going between liquid and gas is 100 degrees Celsius, or like 232 degrees Fahrenheit. So yeah, if I heated this room to 150 degrees Celsius, water would now be in the same type of form as CO2. And then CO2 has very, very low boiling point. So the room would have to be very, very, very cold to get it to go into a liquid or a solid. So, fun to think about that. What patterns are used for naming compounds? So carbon dioxide, right? If I say if I didn't have any of this up there, and I said carbon dioxide, could you draw it? How? So if carbon's up front, it's going to be in the middle. We discussed that last class. So you'll start seeing that more and more often. What about the dioxide? Two. So even though in alkanes we discuss F being for two, when it comes to these types of namings, di will tell you two. So carbon in the middle with two oxygens on either side. Okay. Water is an exception because nomenclature, but if we were to name water, it would be oxygen dihydrogen, dihydride, something like that. But we typically, I agree, it would be, yeah, but on the way that we're about to learn, but it's because it's an exception. So it would be dihydrogen monoxide. Okay, so binary covalent nomenclature wrap up. Previously, we had the alkanes. If you have this sheet in front of you, it shows you the alkanes, the meth, the F. That is only when you have carbons and hydrogens. So if I was to say, let's do C9, how many hydrogens are after C9? So 2 times 9 is 18 plus 2 is 20. What is the name of this? Huh? No name.
Yeah.
No, you're right there. You're on it. You're on it. So there is a lot, but if you look at the sheet that I passed out, there's not gonna be a lot in the beginning. So previously for methane, it would be meth for one, but now we're gonna do mono. Which I think is more like obvious to us if it's one. 2 will be di. 3 will be tri. We have tetra. Penta. Hexa. Hepta. Octa. Nona. Deca. So I think the first 4 are the only things different when it comes to naming alkanes versus covalent nomenclature. Okay. So I do want to point out, if we start naming things, if I throw in an alkane like this, go back to how we named alkane and name it like we're doing it now. So it's set naming, we've already discussed it. So I might throw it in to try to trick you in a way. So don't just kind of use your little cheat sheet, the cheat sheet that says, is this an alkane? Down. Is this something else? Down. So use this while you're learning.
Is that the fix for the first element or the second?
Say it again?
That is the first for the second element.
Both.
Well,
There is an exception, but it's going to be for both. Great question. So these are exceptions. Now, dihydrogen monoxide, I'm going to say water. So if I say water, you're going to say H2O. And then NH3 is ammonia. It's a very basic material that we use for cleaning. It smells awful. But yes, so these are exceptions. If you see ammonia, typically as we get more comfortable, I'll start saying like ammonia and then NH3. But as you get into Gym Chem and beyond, we might just say ammonia. Ammonia, NH3, exception, water, H2O. So do not try to name these in naming them. I do like this picture though, because this is, what is this macro scale, micro scale, or symbolic? The pictures. Macro, micro, symbolic.
well,
So symbolic would be up here. So yes, technically the symbolic is on the screen because it's showing you the formula. But what about these pictures? I think someone got a comment. Yeah, Laura, I see. So this would be macro because it's what we're seeing with our eyes. And then if I didn't have a picture, like if I was to put it out here, that's how it would look. So the ammonia would be a nasty smelling liquid, but it still would be clear inside of a container. Micro would be like if I was to do the H2O or the NH3, that would be micro because it's like part of the water. So all of the naming we're going to be doing. So the alkanes are definitely covalently bonded because they're all nonmetals. Carbons and hydrogens are alkanes. They're going to be in the giant umbrella of covalent molecular bonding. What's different is, since those are just carbons and hydrogens, we're going to move on to everything else. So if it's nonmetal plus nonmetal, it's going to be named how we're going to start naming them with the binary covalent nomenclature. So I just don't want y'all to get tripped up by that. I might throw that in as a, like, let me test you if you remembered alkanes versus non, but like I said, this cheat sheet will help. So it's everything else, but I want to highlight that that is all non-metals. I'm not doing metals right now. Let's get some practice in. Before we get started, I want to put some tips on the screen. First, we don't use mono if it's the first element. If it's the first element has different numbers behind it besides 1, we will use the prefixes we discussed. But if the first element is by itself and only has one of it, we don't use mono. And the second tip, you're going to end the second element in I. These are fun. So if I were to look, this looks like if, it's not if, it's just iodine plus fluorine. So on the first one, you always write out the first element as is. So this one, there's a 1 behind it, so I don't have to write out mono. I'm just gonna write out iodine. We don't add I because it's the first element. We just write it out as is. If there was a 2 out front, yes, but how many fluorides? How many fluorides?
1.
Yeah. I know sometimes they would say like iodine fluoride because it's like a shorthand notation, but for this one, we're gonna try to be as exact as possible. And so I would prefer iodine monofluoride. You put the mono on the second one always, if it's by itself, yes. You just don't put it on the first one. Yeah. All right, let's look at the next one. It's IF3. What is the first element? Iodine. Do I need to put mono? Nope, so iodine. And then how many fluorides? So what I'm gonna put up front? Try. IF5. So we still have 1 iodine, so I'm gonna iodine. How many fluorides? So what is the prefix? Penta, yes. That would be, this little rule would be for this first bit. For the next bit, you have to use a prefix if it's not a 1. So how many, so that element there, that S is sulfur, how many sulfurs?
2.
So what do I put as the prefix?
Nice.
Disulfur. So in this one, we don't add "ide," we leave the element name as is. So disulfur. And there are 7 oxygen. So what's the prefix? Now, when I was doing this, I was like, okay, this one's kind of confusing. Is it heptaoxide? They technically don't put the A at the end of hepta because the O, it's kind of like vowel. They took out the A and just did oxide. So it would be heptoxide. But at least we'd still know hept means 7. What about the last one? What do you think? Yes, the last one would be an example of me trying to trick you. I'm throwing that in there because, you know, you're working hard, you're trying to learn these new concepts, but this one is only carbons and hydrogens. I just want to test you. Are you remembering your alkanes? There's a 4, so 4 is butane. Great job. So if I was to throw something like this in the quiz, be ready for that, and definitely would have your little cheat sheet with you. So now we have a break in 6 minutes, but I'm gonna get us started. So we'll probably do like the next 6 to 10 minutes, maybe like. You don't have to do it through the break, but I'll just do it after the break too. I would like everyone to get out their worksheet. If you are online, download it so you can start working on it. And we're gonna one to turn the page to the back. And I want you to put at here. I'm gonna get this up in a bit and I'll show you, but I want you to put at the very bottom, C8 H18. And then like put a box around it to like at the very bottom.
Little box.
below the box, like add one more. And then y'all can get started. So on the second page in the back of it, put C8, H18, and then put a box underneath. I'll put that up here. And then we have another 5 minutes. No, wait. The break? No, we have 15 minutes. Sorry. We'll do this until the break. Sorry, I have my alarms to remind me in case like I start doing things too soon. But we'll do this until the break, and then after the break, we'll move on to the next thing. So at home, what I was saying, add.
Where can I find this worksheet?
Yes, it's under the Unit 1 module, under 1.4. So add that to the end of the second page. No, worksheets are not a grade. It's just a way for us to practice in class and also give you a break from listening to me talk. So I think they're a lot of fun. So typically I'll give you the worksheets to work through, and then we'll go over the answers and then move on to the next one. If you were doing 1320 during a regular semester, yes, it would be incorporated into your grade. You're welcome. I'm hungry too. During lunch, I hope if you get hungry during exams, you can eat too. We work with this? That's why I know them. Really interesting stuff. It can make us. Oh, we do that. Like, I struggle with acronyms. I work in the chemical industry and they acronymize everything. And I'm like, my brain doesn't memorize like that. I hate acronyms. That would have been helpful. I don't know. Y'all have to deal with acronyms like at your jobs, because I hate them. Used to. Like everything we would do is acronyms. So if you like the Brinkelhoff, good, but I don't do Brinkelhoff. Let's, for this summer, let's bring them back. You should do YouTube videos and get like paid a lot of money for making like help. We could bring it and like get them some good viewership. If anyone gets stuck, please don't hesitate. I'll come directly to you if y'all have any questions. But don't hesitate to try to kind of come up with your own. I know that this seems like I'm asking a lot of redundance, trying to have you do like an essay style question. But you really want to think about these things. What do you see in common? And try to make yourself a cheat sheet, especially like up here. Try to like maybe word in a way that would help you figure these things out. And once you're done, you can either take a mental break and do whatever you want, or if you want to get your homework up and maybe look at those homework questions that are similar to this with the downtime, you're welcome to do that always.
Where can we find the homework?
So go to our Canvas site, under modules, there's gonna be something that mentions Achieve in there. I double checked all those links, so you should be able to access Achieve through any of those links. So click on it and make sure that you connect the site to our Canvas. And then, but you can access the homework through that.
Is it under, ebook?
Under what?
Is it under ebook?
Yes, it'll be ebook and Achieve platform, yeah.
Doesn't actually show up on the week 3?
Yes,
It's 2, okay.
yes. So just because it's due on Friday of week 3 doesn't mean I don't want you to start now.
Got it.
Yes. Save yourself stress. Yeah, so I do think that there will be downtime after the end of, like, towards the end of class where we'll work on it together. Okay. Let's go over this real quick, and then I have a few slides of 1.5 to go over with you, and then we'll take the rest of the downtime to look at the homework. So here is just some examples. These are really good for like helping us kind of see how other types of naming would work. So carbon monoxide, even though there's a one oxygen here, you still have to have the mono only on the second element. On the first element, we never add the mono. So carbon monoxide to dioxide, dinitrogen monoxide. So yes, because there's 2 nitrogens, you have to have the di out front. But yeah, so you go through it and you look and see all the different types of naming. And it says, what patterns do you see connecting the formulas and the names of these compounds? So I might have already said it, but I'd love to hear from your perspective. What patterns do you see? If you're a little shy, I would start by looking at the last 3 letters of every name.
It's something.
Okay. What about the first element? Does that one end in I? What is the name of the first element typically?
Just.
Yeah. Okay. Maybe let's look at the first element. Do we include mono? Okay. Let's look at the subscripts. So subscript is the letter, the number that comes after. Prefix is the, I guess, what comes out in front. Do you see a pattern between the subscript and the prefix? Yeah, I know I'm being redundant. I just want to hear it. Sorry. Okay. Let's look at the compounds, the elements. Do you see a trend? Are they all one thing? Are they metals, non-metals?
All.
Okay. So yeah, this naming is only going to be with non-metals plus non-metals, with the exception of alkanes. So none of these are alkanes.
Third one second.
Huh?
No, what is that?
Oh yeah, sorry, my handwriting's not very good. So no mono for the first element. So that's like, I'm pointing out, like carbon monoxide. You have to have mono for the second one, but not the first. Any questions on that? I'm gonna leave these first two blank, but that's just how you can develop like a little how-to. So like if I was to say develop a procedure to write the name of the compound from the formula, I would first maybe say, is it an alkane? Are they all non-metals? If they're all non-metals and it's not an alkane, well, what do I do next? Okay, I would look at the subscripts and assign a prefix with the exception of the mono. I would probably like make a little cheat sheet for myself. Same thing with the next one. So I'll leave that one blank. If you want to see what Dr. Patterson wrote, the key is available to you under module 1, unit 1. I always will give you the worksheet with the key at the same exact time. So let's do practice 3. I'll let y'all just kind of tell me as I write, what are the prefixes? This is not alkanes. This is for the binary covalent. So what is 1? Okay. Yeah. Uh-huh.
Three. Excellent.
Awesome. Okay, now we're gonna actually put everything together. So we have them saying it out for us and we have to create the formula, or they give us the formula and we have to write it out. So we have phosphorus trifluoride. So say it. P, so phosphorus is by itself, no mono, but it's still by mono. And then trifluoride. So 3 fluorides. And then we have N2O4. What's the prefix? Yeah. Once again, because of that O, we kind of take out the little tetra. It's just tetroxide. Right? What about oxygen difluoride?
OF2.
OF2. Okay. IF7.
Iodine heptafluoride.
Oh, I did chloro instead of fluoride. Sorry.
Yeah.
I don't know. It's writing here. It froze. Sorry, guys. How do you unfreeze Zoom? Let's stop share. Okay, let's try going back. Sorry, now you can see my messy handwriting. Okay, so carbon tetrachloride. So let's start with carbon. All right, chloride. Yeah. All right, P2O5. Mm-hmm. Perfect. Dinitrogen tetrachloride. Okay. You know, why isn't it mononitrogen? Okay. Tetraphosphorus trisulfide. Mouthful. Or S3. Perfect. And then SI is for silicon. So what is that one? I think it's for 2 L's. No, doesn't look right. And the last one. Octane. Don't try to name that one. It's just octane. It's an octane.
We were to make the mistake of like putting the A and the O in the same. Will we get points on for that or?
Like here with like putting an own.
No, like tetroxide.
Oh, you wouldn't get points. You would lose all points because we talked about naming alkanes and then with the cheat sheet, it kind of helps you go through, is it an alkane versus, so it's more of just getting you more and more comfortable recognizing the difference. So yeah, unfortunately, it wouldn't be correct. How do you feel about that? Yay, okay. So I'm gonna move on to a little bit of 1.5. And then of course, if you don't have your computer, we're gonna hit homework after. All right, I'm just gonna go up until accuracy and precision because 1.5 is a little hefty of a section, so we'll probably handle the rest of 1.5 next class. So yes, significant figures, scientific notation, but it does have a little bit of accuracy and precision. Numbers are very, very important in chemistry because when you get into a chemical lab, you start having to deal with things that have measurements and we have to do math based on those measurements. So it's important to push you to be able to utilize those numbers in the correct way. So procedures that chemists use when handling measurements. It could be as easy as taking a beaker to measure a volume. Technically, we wouldn't want to use a beaker because it's just not as accurate. But they have different devices that can measure volumes more accurately. It could be going to a scale and weighing a weight. So we use procedures and we have specific numbers that are relevant, so significant. So we use precision and accuracy and most important, I mean, they're all most important, to be honest. So significant figures and digits. So we're going to hit on sig figs towards the second half, so next class. And then today will be precision and accuracy. So there are procedures for handling really big and really small numbers. I do want to point out that when you work for like bigger corporations, you think that going to a scale and making a measurement would be just too easy, but they have procedures for everything, especially for safety. But I'll tell you now, like if you work for a bigger company, like they're gonna have a procedure for every little thing that you think is the easiest. Why do you do it? They haven't, because it's all important and it's all significant. And then big numbers and small numbers are also very relevant. So being able to use scientific notation. So we're gonna get into maybe how to use your calculator with scientific notation. So that would be like me typing 2.0 times 10 to the 5th or 10 to the minus 5th. So that would be the scientific notation. Sorry, I'm highlighting the wrong thing. That would be scientific notation. So if it was 10 to the 5th, 2, 1. it would be the same thing. So being able to go between them if you have to, or if it was negative though. And then with and without a calculator. So I was able to do that without a calculator just because I can move around the decimals. So hopefully getting everyone on board with how I did that, that'll be for Wednesday. Ooh. Okay. So measurements, I mean, as you go further and further into chemistry or even in industry, they have all these amazing machines that measure things. But this is just the basic ones that we hit in Gym Chem, and then you keep going and getting better, bigger, bigger, bigger. But I do want to point out there is always going to be an uncertainty in every single type of measurement. And just because you're uncertain does not mean it's not significant. So I love this picture. Let's say they're measuring this disc right here. If you were to start rounding it, it wouldn't be accurate or precise. So like if I was rounding this and said it was 3 centimeters or 2 centimeters, that would be really, really off. It wouldn't be the most accurate. But I still, it's okay to have that last decimal place be uncertain because that's what the measurement wants. So what I am certain of based on this measurement is that I have 2 point something centimeters. And it's up to us to identify that uncertain digit. Now, I might think it's 2.7. You might think it's 2.8. It doesn't mean that we're both wrong or one of us is wrong. It means that we're in the right ballpark and at least we're being pretty precise and accurate. So I would say maybe 2.7. You cannot do 2.75 because there's not more ticks telling us to be more accurate. So that last decimal place has to be the uncertain one. So I can only go up to a 0.7 or 0.8, but we're both right. This one here kind of has, I don't know where that decimal place is. I think it's like 44.04 based on, I think it's in millimeters. I'm just guessing right now, just based on this awkward looking screen. But just note that that last one, even if it is an instrument that's giving you a number, it's still an uncertain decimal place. It might kind of fluctuate a little bit, but when it settles, that's going to be the one you put down and it's significant. This beaker, this is also why we do not use beakers to measure exact amounts of volume, but I would say this one is almost to 50 milliliters. So I would say it's 40, I don't know, I could say 49. I cannot do 49 point something because there is no more ticks telling me to be more accurate. So that last decimal place has to be your uncertain one. So this one's not a decimal place. The last digit has to be your uncertain digit. So because this one only does 20, 40, 60, 80, then that 9 is the uncertain digit. So if you think it's 48, we're both right. But we have to include that because I can't just put 50 and I can't put 40. This is what we call a graduated cylinder. This one's a much more accurate way of measuring volume. So in this case, like I could say, this tick, like it looks like it's hitting exactly 47.0. And I have to include that 0.0 because it is significant. So it looks to me that like it's hitting the 0.0 mark exactly. I can't just put 47 because you have to include that last one, that last uncertain one. So it could be 0, but you have to include it. So these are just really good examples of different types of measurements that need that last digit. Precision describes how fine the divisions are on a tool, so how close the numbers can be to each other. So I hate beakers. Beakers are holding vessels. They are not measuring vessels, but they're not precise. They're not accurate. They're just there to hold an approximate sum. We don't use them for measurements. So they're neither accurate nor precise. So let's get into this because I feel like it seems very redundant, but when you get into chemistry, knowing the difference between accurate and precision is very important. Especially, I guess when I teach quant, I like to teach, so I'm an analytical chemist, so statistics and analyzing results is like my niche, love it. So that's why I get very peevy when like the numbers are just way off and a student will write up a lab report and say, my data was accurate. And I'm like, you don't know the right answer. You can't say that. So it's just, that's my little niche. It's just, you got to be able to understand the differences. So precision is being able to consistently hit around the same number. You don't have to be accurate, you can still be precise, but it's being able to consistently get around the same one. And then potentially with a lot of digits, like how, like, small can you get it? How close you can get. Accuracy is just about in the ballpark of how close you are to the right answer. So I would like to point out this, if I was to average this one, it would probably be like, I don't know, really, really close to the middle. So yes, it is accurate, but it is not precise, because if I was to average them, it is very close to the reliable goal, the center, but it's not good. So this one is showing both precision and accuracy because it's hitting the same mark every time, and that mark happens to be our goal, the middle. This shows me that there's probably something wrong with the person's, I don't know if this is a gun or if it's like a bow and arrow. There's something wrong because they're hitting their mark very, very well. It's just off. So maybe they need to fix something to get back to center. That's precise, not accurate. This one's neither, just someone just needs to get a lot more practice. But yeah, for this one, you can definitely be accurate and not precise. For me, that's when I would average them. That's how you can tell. Let's talk about numbers if I was in a lab. Oh, sorry, I forgot to put it back to me. Hi. All right, let's talk about numbers if I was going back to a lab. Now, sometimes we can just look and see. This should be bigger, but like this is our answer. This is the correct answer, what I highlight. If I was just looking at numbers, sometimes it's a little bit more difficult. So I'm going to start with the easiest one. If I was to ask you, is this accurate? Do you think this is accurate? Not accurate. Is it precise?
Yes, person.
Yes, because if you look at all of these numbers, they are very, very close to each other. So it tells me maybe it's not even the chemist's fault. Maybe the scale's messed up. But they're measuring things pretty well. They're just close to each other. It's just not accurate. Okay. With the other ones, sometimes for me, I like to take the average just to see how far off from the middle we are. So if I was to like, let me get a different color. I'm gonna put the averages for these at the very bottom. So 26.3615, 26.38, 26.856. All I did was just add them up, divide them by 5. But let's focus on this one. If the answer is 26.3615 and the chemist got average 26.3615, and what do you think? Yes, I agree. It's both precise and accurate. They were hitting 26.361 every single time. So that one is definitely accurate. That's a good chemist. This one, if the scale is going to measure to 4 decimal places and the chemist rounds, not good. Like you can definitely be accurate. I would say this one is accurate because they're averaging around 26.38. But it's not precise because the chemist is cutting off and rounding. You never want to round. If the scale is spitting you out numbers, all those numbers are significant. So this one I would say is accurate, but not precise. Does that make sense? Does anyone need me to explain that again? Okay. Don't round. Honestly, I'm very picky on that because my classes typically are accuracy-based classes, and students who round way too soon, they ruin their accuracy points, but this is 1320. But I typically don't round until the very end. So like, let's say you're doing math and you round too soon and you're doing one of my quizzes or my exams, that might prevent you from getting the right answer because you rounded too soon. So just don't round until the very, very end. Okay. And we'll hit significant figures in a little bit. I'll tell you how to pick the correct one, but in this case, just don't round ever a scale. So it's accurate, not precise. I can't spell. All right, this last one, is it accurate? It looks like it at first, but if you look at the average, is it accurate? Is it precise? No, this one's neither. That's what I'm saying, like, when you look at it initially, you're like, well, it could be, but that's why the average will kind of be obvious to you and say, okay, it's way off from our expected value. And all these numbers are way off from our expected value, this one's neither. So that one, just because maybe the chemist is trying to cut corners or just not really. This is an example of, like, let's say I told the chemist, I want you to measure 26.3615, and they were kind of all over the place. How do you feel about that? I do like to ask questions like that where, like, I'll give examples and I'll say, like, what category is accurate, most accurate? What category is the most precise? Like, you can kind of, if I was to give you maybe something like this on a quiz, could you answer it? If you can't, no worries, come back to this, or, you know, come to my office hours, we can work on that. Okay. I think this is the last slide I have. So procedures for communicating the precision with which measurements are made. So that'll be, if a scale measures to 2 decimal places, you have to record it to 2 decimal places. Some scales will measure to 4. You have to record it to 4. So that's how you can be both precise and accurate. There are procedures for helping you become more accurate. Like, for instance, do you know what the word calibration is? We use calibration a lot. Like, let's say you want to step on a scale at your house. You want to make sure your scale says 0 before you step on, because no one wants to be on a scale that's not calibrated. So you might step on it, it'll say CAL, and it'll calibrate, and then you can safely and get an accurate weight. So that's how we can calibrate it to make sure our results are both accurate and precise. So if you did it again and again and again, you get the same number. So calibrating is a great way that we can make sure our measurements are both. So it helps maximize the precision and accuracy. Limiting precision, I guess, would be making the measurement smaller and smaller. Any questions about accuracy and precision? Awesome. So with the rest of class, let me stop share. I'm gonna stop recording, but I'm gonna still keep talking.